In the next section, we're going to discuss the special properties of water. So we've got a couple of objectives that are concerned with the special properties of water, the things that we need to know about the water molecule. Remember, and that's shown on this next slide too, remember that water molecules are dipoles, that the hydrogen atoms are relatively unable to hold on to electrons, so they have a delta positive charge. The oxygen atoms are really good at holding on to electrons because they're so electronegative, and so they have a net negative charge. So the dipole of water is represented in my view by this this Mickey Mouse hat that I'm wearing. So you have to scrunch down so you can see my Mickey Mouse hat. Okay, so here's the positive end of the molecule. Okay, so this is positive up here. Okay, this is the positive end of the molecule because this is where the electrons are not. So this is the positive end of the molecule. Down here is the sad negative end of the molecule. So this end of the molecule is really sad because this is where the electrons are hanging out. It's a really negative part down here. Okay, so negative down here, positive up here. That's what we're seeing. That helps you remember. I know that's pretty silly, but it helps you remember the structure of the hydrogen or of the water molecule and where the net negative charges and where the net positive charges are. So this is a special property of water, that each water molecule is a dipole. That means two things. Water forms hydrogen bonds. The hydrogen atoms, the hydrogen atom into the water molecule has a partial positive charge. The oxygen atom into the water molecule has a partial negative charge. Those opposite charges attract in hydrogen bonds, and so water forms hydrogen bonds. That's property number one that's really important. The other property of water we mentioned earlier is that water dissolves stuff. It does that by forming a shell of water molecules with their partial negative charges, as shown up here, surrounding the total positive charge of the sodium. The sodium has long ago given away its electron, so it has an excess number of protons. It has a full positive charge, and these partial negative charges all surround this sodium atom and the sodium ion and cancel out its charge. So 1/5 of a negative charge in each of these, 1/5, 1/5, 1/5, 1/5 in this diagram, all make up a negative charge that's going to screen out and cancel out this positive charge in the sodium. We call this a hydration shell or a hydrated sodium ion. The opposite thing is going to happen, the opposite orientation of water molecules with a chloride ion. Remember, this permanently has grabbed an electron from that sodium atom, and so it's permanently holding on to that electron. And as it permanently holds on to that electron, it's got partial positive charges of water screening it out. And so sodium chloride, when it dissolves, tends to order water molecules. It tends to impose an order on them in these hydration shells. Because water molecules attract each other with hydrogen bonding, and these bonds slip and work past each other because we're in a liquid state, but because there's this high degree of hydrogen bonding within water, then water molecules attract each other very strongly, and that gives water a property called surface tension. If I fill up a glass with pure water, I can let the water come up over the rim of the glass because of this property of surface tension. This is important in human medicine because we need to secrete a product in our lungs called surfactants. And a surfactant is the same thing as a soap. You may have noticed that if we add soap to the water that's mounted up over the top of a glass, that we actually destroy its properties. So if we have like a little droplet of water, which forms a little round thing, and we add soap to it, so if we have a water droplet like this, which has surface tension all along its surface because of the hydrogen bonding of the water molecules, and we add soap to this water droplet, then the water droplet is just going to fall apart. It's just going to form a sheet, a layer of water molecules. So by adding soap, we know that we destroy the surface tension of water. Surfactants reduce surface tension. We can also use surfactants in order to pick up grease molecules, but that's another story for another day. In human medicine, we use surfactants in the lung to reduce the surface tension of the lung. The water molecules in the lung would have enough force between them because of the hydrogen bonding to actually collapse the lung if the lung didn't secrete surfactants. This happens in premature babies, and so in premature babies, because they haven't started to secrete their own surfactant, we have to supply them with a surfactant, and so we give the premature babies an artificial surfactant so that their lungs can inflate so that they can breathe air. The other property that comes out of the surface tension of water is what's called capillary action. If I put water in a tube that is fairly narrow in diameter, then the water seems to be pulled up into the tube. We use this with hematocrit tubes, they're called, for picking up blood. If you've ever given a small droplet of blood and you notice when that narrow glass tube came close to your finger with the droplet of blood on it, that it seemed to suck up the blood.
Insert the capillary tube fully into the blood, holding it in a horizontal position. This will allow the capillary action to draw the blood into the capillary tube until it is 3/4 of the way full.
That's because blood, because it's mostly water, has a great deal of surface tension. And that's a property called capillary action. It's because all along the surface there's surface tension. There's greater surface tension in this region here than there is between glass and the wall of the container. So the net effect is to pull the water up into the tube.